Okay, we're going to look in this screencast at implicit differentiation. So we're continuing this epic section on differentiation, and done a lot of stuff, haven't we? We've been differentiating different types of functions, product quotient rule, looking at optimization, turning points, all that sort of stuff. Now we're going to have a look at something known as implicit differentiation. Let me explain what that means. Now, functions can be either explicitly or implicitly defined. Now, this one here, because it's y equals, y is the subject. We would say this is an explicitly defined function. Explicitly defined function. It's explicit because it's clear y equals 2x. Now, if we take the same function and say y minus 2x equals 0, same function, but we'd say that now it is implicit. It's implicitly defined because we don't have our x or y as the subject. So that's an implicitly defined function. So when we are working with our functions and looking to differentiate them, then this has a bearing on how we go about it, whether a function is implicitly or explicitly defined. Now, to this point, this is what we've been dealing with. We've been presented with explicitly defined functions. So let's run with y equals 2x. If we want dy dx for y equals 2x. Okay, so find dy dx is the task. Find dy dx. Find dy dx. Then let me present it to you in a slightly different way. What I'm going to do is look at deriving with respect to x both terms. So we're just going to run left to right and derive with respect to x all the terms in this function, of which there are two. So on the left hand side, what I'm going to say is I'm going to say, therefore, for y equals 2x, I'm going to derive with respect to x y, all right, and that's going to equal the derivative with respect to x of 2x. Right, so this is what we're going to say now. This is not in terms of x, so I can't simplify this at all. I just write it as dy dx. This, however, the derivative of 2x with respect to x is 2. So dy dx is equal to 2, and that's just saying the derivative of y with respect to x is 2. So just thinking about it in a slightly different way, because now I'm going to show you over here if we did the same thing. I'm going to leave it as an implicitly defined function. I could make y the subject, make it explicit, but I'm going to leave it as an implicitly defined function. I'm just going to work from left to right and deal with each term. And so from there, I'm going to derive with respect to x y. I'm going to subtract the derivative with respect to x of 2x. And that's going to equal the derivative with respect to x of 0. All right, so let's work through these. The derivative of, that's just dy dx. Minus the derivative with respect to x of 2x is 2, and the derivative of 0 with respect to x is just 0. And if we make dy dx the subject now, dy dx is equal to 2. Same result, whether it's been implicitly defined or explicitly defined. Okay, so there are plenty of functions. That's a fairly straightforward one, obviously. But when functions become a little bit more complex, then yes, we can make them explicitly defined, but sometimes it's easier just to leave them implicit and just go through and find out dy dx. Let's do an example of, say, the equation of a circle. So find dy dx for the function, and this is an implicitly defined function, x squared plus y squared equals 1. The old circle, center, naught, naught, radius 1. Okay, find dy dx. Okay, well, let's then derive with respect to x every term as we just move from left to right. To derive with respect to x squared, ddx y squared, ddx, we're just ddxing everything. Right? We've learnt from day dot that when we've got a function, it's okay to do stuff to it as long as you do the same thing right throughout. So yeah, we can multiply by 2, divide by 2, add 1 to both sides, take the log of both sides, add them to, we can do lots of stuff. Another thing we can do, we can just ddx every term. All right, that's fine. So now we're taking, well, in order to find the derivative. So that's ddx right through here. The derivative with respect to x of 2x is of x squared is just 2x. So this says the derivative of x squared with respect to x. Now, because we're deriving x squared with respect to x, the variable that we've actually got this function, then we derive it using the derivative rules, 2x. But when we've got derive y squared with respect to x, well, we can't do that. We don't have we can't derive y squared with respect to x. What we can do is use the chain rule to get around this. So let's look at, rather than working through, let's work through dy. So we use the chain rule. So d dx y squared is the same as the derivative of y squared with respect to y by dy dx. Can you see those dy's remove each other? So we end up with dy squared dx, which is what we've got here. So we're just using the chain rule. Now what this is equal to, the derivative of y squared with respect to y is 2y dy dx. So this deriving y squared with respect to x becomes 2y dy dx. Okay, so this, if you have a look through now, that's my second term, and the derivative of 1 with respect to x is 0. So what we've got is therefore 2x, that's not equal sign, that's going to confuse things, 2x plus 2y dy dx is equal to 0. From here we can make dy dx the subject. So this term easy because we're deriving with respect to x, that's 2x. But when we've got an expression in y which we want to derive with respect to x, then we can use the chain rule, or as we're going to do in the next example, sometimes the product rule. Use one of our differentiation rules to work it through. So yeah, I can work out derivative of y squared with respect to x. I can run it through a dy. So I can find the rate of change of y squared with respect to dy and multiply it by dy dx, and that's going to give me the same outcome. So, but the advantage is that I'm going to get rid of this dy squared dy squared dy. That's just 2y by dy dx. Now look at this. I can make dy dx the subject here by firstly subtracting that 2x, and then secondly dividing by 2y. So dy dx is equal to minus 2x over 2y, or just minus x over y. So there's my derivative, and therefore, what we've got here is a circle, and I can now find the rate of change, or the slope of the tangent. Let's go for a point. This is 1. So let's go for a point at x equals a half, say. So the dy dx at x equals a half is equal to minus a half over y. And when we've got x equal to a half, we've got x equal to a half. What's y equal to? This is x squared plus y squared is equal to 1. When x is a half, that gives me half squared to a quarter. So y squared equals 1 minus a quarter, which is 3/4. So y is equal to the square root of 3 over 2. So I can say that that's the square root of 3 over 2. And this times top and bottom by 2, you get minus 1 over the square root of 3. That's going to be my dy dx at x equal to half, for instance. And does that looks about right? That means the slope of my tangent at that point is equal to minus 1 over root 3. Okay, let's do one more. So find dy dx for the implicitly defined function. Let's go with 2xy plus 3x plus y is equal to 4. All right, we've got stuff all over the place here. Okay, so let's we're finding dy dx. So we're just going to d dx 2xy. We're going to d dx 3x. We're going to d dx y, and we're going to d dx 4. Okay, that's finding that's going to help. That's going to get us to find the derivative, finding dy dx for this implicitly defined function. Very difficult here for us, isn't it, to make it an explicitly defined function? So much easier to go through and deal with each term as we go. Now, in doing so, we've got this 2xy. We're going to treat this 2xy as a product rule. Okay, so what we'll do is we'll derive. So we'll just go off to the side here. What we'll do is we'll take the derivative with respect to x of 2x. So we'll find d dx 2x and just multiply that by y, plus, now what we'll do is take the derivative of y and multiply that by 2x. So that deals with that term there. d dx 3x is easy. d dx y is just dy dx. And d dx 4 is 0. Okay, so the derivative of 2x with respect to x, that's 2, so I end up with 2y here. So 2y here. Now this is dy dx times 2x, so that's 2x dy dx plus 3 plus dy dx is equal to 0. Okay, we want to isolate our dy dx's, so therefore I'm going to factorise my dy dx's out, 2x plus 1, and that's going to equal minus 2y minus 3, and so therefore dy dx equals minus 2y minus 3 over 2x plus 1, and that's my derivative. Okay, let's look now at questions from exercise 4t, which is on page 220, and we'll have a look at those in class. See you soon.